Today my presentation is about urban soil health and the tree performance, a diagnostic framework, and the biochar inactivated is the case study. So, so this is the contents of my presentation, and there are 5 parts in my presentation. And I'm gonna quickly go through the background of urban forestry and urban soil health, and provide with some soil amendment options, and more focus on biochar. And then I'll discuss a greenhouse experiment we did this year. So I'm gonna start with a brief history of urban forestry, which is actually definitely not a brand new concept that can be traced back to late 19th to early 20th century. And the key milestone came in 1974 when Eric Jorgensen, who was also a very grateful professor in our faculty during 1960s. So he defined the concept as an intergradient measurement, delivery, ecological, and social benefits. And more recently, organizations like FAO have bordered the concept even further. So Toronto, I think most of us know that we have a target of 40% canopy cover by 2050. And that sounds like a tree problem, but in practice, it's pretty much a soil problem. Soil is a foundation of the urban tree performance and of many ecosystem services. For example, like cooling, stormwater management, carbon storage, and so on. But typical urban soils are often extremely degraded from physical, chemical, and biological perspectives. And here I want to highlight that the compaction, which is one of the most serious and widespread issue in the urban context. So the plant roots are squeezed into very small volume of soil with high bulk density and surrounded by impervious surfaces, which limits the rooting depth, oxygen supply, and water infiltration. So the fact, oh, so is that bad? Okay, so the fact is that even though we pay a lot of attention on tree growth, the poor soil often make it very hard for tree to survive and grow well. And when we talk about soil health, it should at least include soil quality and fertility. And we usually group those indicators into 3 broader categories: phytochemical, biological, and sometimes functional. And in urban forestry, we tend to focus heavily on the physical and the chemical side of the urban soil, but sometimes like ignore the biological layer, especially like microbiome function. But soil microbiomes are actually central to the nutrient cycling, soil organic matter turnover, and of many key soil and environmental processes. So if we only look at the outer sign of the soil health, like for example, like just like texture or something, we actually still miss a big part of why some soils can sustain healthy tree, but others cannot. And given those soil constraints, we have already applied a lot of soil amendment options. And on this slide, I highlight 3 very common options that we already applied, and you might easily observe when walking on the street. So organic mulch, compost, and mineral fertilizers. And there are a lot of studies have already proved that the efficiency of those sort of products, but there are also some sort of drawbacks of each of them. For example, like the compost and the mineral fertilizers tend to increase the soil EC, and consequently might increase the risk of plant physiological drought and iron toxicity, and also some sort of runoff risks. And for the wood mulch, there are some risk of oxygen deficiency in the rooting zone, and also might increase the pathogen risks to the plants, especially when the operation were conducted and not correctly. And in addition, Sean's team just published a paper pointing out that wood chip might emit methane and possibly convert the soil from carbon sink to source. So which is definitely not a good for the city's carbon budget. On this slide, I provide with some relatively new options here from a lot of studies. So catechins basically act as a biostimulant, activating plant stress response signaling, and also adjust the hormones to improve plant growth. And at the same time, some research also found that catalysts can absorb microplastic, so potentially reduce microplastic pollution in the urban context. And spent mushroom substrate is, which is very similar to compost, slowly release nutrient and improve the soil structure. But the most important thing here is that it already contains some sort of fungi and microbial communities, which may boost the soil microbial activity and improve plant growth better. And PGPR is for sure plant growth permitting bacteria, and a very common example is ribbium, which promote nitrogen fixation and improve nitrogen utilization of the plants. But a common problem of those sort of products is that the studies of them are still, most of them are still in the agricultural context. So there's limited information for urban forestry use, and which means a higher uncertainty if we apply that one. So biochar is a carbon-rich solid produced by pyrolysis of biomass under low oxygen condition, and because of its porous structure, stable carbon skeleton, and surface functional group, it has a great potential for soil man application. And the mechanisms basically can be summarized by those 5 processes over there. And the very key advantage of biochar is its long-lasting and the structural scaffold. So we can put one or more other soil amendment in biochar to provide better beneficial effects. For example, there are some products like a biochar-based microbial inoculant or like a seed coating or stuff like that. So when applying biochar in urban context, there are 3 key benefits associated. As I mentioned, compaction is one of the most severe and common problem in urban content. Biochar has a high physical stability, which is hard to break down. So applications can mitigate the compaction and reduce the bulk density for long term. Secondly, urban soil, especially street tree peat, are heavily rely on external nutrient input. So biochar's porosity and high CEC helps water and the nutrient retention, which helps tree growing more sustainably. Thirdly, biochar's microbiome-friendly characteristics can improve microbiome function of the soil. A lot of studies have shown that biochar has a positive effect on nutrient and nitrogen fixing microbiome, like the one I mentioned, rhobium, and also some sort of microorganism fungi. So this photo over there just basically shows biochar's microbes provide with better shelter for some of the microorganisms. But there are also some limitations and the issues of biochar. So one issue is the benefits to the plants are species specific and context dependent. So this graph is from a previous study of Zhang and his team. Basically, this one shows the biochar effect of viral among different species. And another concern, especially in the short term, is nitrogen immobilization. Fresh biochar is can temporarily tie up nitrogen, making it less available to the plant. So one way to address this is to pair biochar with an additional nitrogen source. And Inactivated Yeast is a very good example of nitrogen-rich organic input. Again, a previous study by Zhang and Melanie, they had a very great observation that the biochar and Inactivated Yeast co-application can have a benefit effect on the plant biomass. But that study was focused on several maple. As I mentioned, biochar has sort of species-specific effect. So this brings us to our greenhouse experiment. So we designed the study around the 4 research questions over here. But in summary, basically, we want to kind of systematically analyze the effect of biochar and Inactivated Yeast on soil health and the tree performance. And also we want to compare one local sourced yeast with another commercial product. So to address those questions, we conducted a 4-month greenhouse experiment and using American elm as a target species. We used the slow pyrolysis mixed conifer biochar and 2 types of yeast, as I mentioned. One is from the Lemon, a French company, and a commercial soil amendment product. And but that one is no longer selling right now. So then another one is from our local source a local boreal residue, Bellwood's company. And we DIY the yeast heating at 80 degrees for 24 hours to inactivate the yeast and drying at a 60 degrees for like 5 to 4 days, and then grind it into 2 millimeters soluble dry powder to make it more desirable for application. And we also applied the de-icing salt to better stimulate the real-life situation in the city of Toronto. So we use the common road salt products, which contains majority of sodium chloride. And we measure the indicators some over there. And for the microbial activity, we measured using a biological ecoplane method, which perform a community-level physiological profiling of soil microbial functions, communities. So some sort of functional diversity analysis. And basically, each plate has 96 wells, which include 31 different carbon sources, and with 3 replicates and 3 water control wells. So each well has a dye in it. When the microbials from our soil sample use a given substrate, the dye changes the color. And based on the depth of the color, we can analyze the different utilization of a given substrate. And the advantage of this method is it is low costing and standardized and scalable, but it also has a bias toward fast-growing bacteria. But here, however, this might not be a big issue in urban context because like urban soil, which are often heavily disturbed and the fast-growing opportunistic bacteria can really dominate the shorter nutrient cycling. So ecoplay might actually quite relevant for understanding the functional responses of different soil amendments in the urban context. So the results of our greenhouse experiment, I'm gonna focus more on the soil part, and Zhang will discuss more on plant responses. So biochar application slightly increased the soil pH from 8.3 to 8.5, and Inactivate is tended to decrease the pH, and that might be because of the original pH of the Inactivate yeast is only like 5 to 6. And for the soil yeast, salt is the only factor that significantly increased the yeast, and biochar tended to lower it. At the same time, we observed the soil organic matter significantly higher in the biochar applied groups. And a possible reason is that because biochar acts as a direct input of organic carbon to the soil. And at the same time, biochar also might improve the fine root turnover and steadily supply more below ground litter and subsequently increase the soil organic matter. And for the microbial activity, we observed that biochar plus Inactivate is the combination significantly increase the AWCD, and the effects can be basically ranked as here, the IYM, which is a local one. So the one reason for that is basically we've already talked a little bit, like biochar can provide a better microenvironment for the microbials. But another very interesting result was the local yeast plus biochar co-application, which showed the best performance. So and it even contains less nitrogen compared to the commercial one. So which might indicate that the local one might have a better interaction between with biochar. So for the plant responses, I'm not gonna go deep here, but we did observe significant increases on plant height, leaf area, and total biomass. And one point I want to mention here is that our leaf pigment measurement of the we did observe the chlorophyll content decreased in biochar applied groups, as you can see from the very right bottom figure, and all the bars with the dashed line are the biochar applied groups, and it point out the biochar causes nitrogen immobilization. But considering the better soil performance, especially like the AWCD, we can still speculate that Inactivate yeast might still mitigate some sort of short-term nitrogen limitation. And lastly, the heat map. This heat map shows the correlation between soil trails and tree trails. And the summary of it is basically the treatment groups with higher AWCD generally has better tree performance in terms of growth responses, gas exchanges, and so on. So take-home message, our result generally supported that biochar and the inactivated yeast is an effective core amendment, and the local brewery yeast worked well as an extra nitrogen source, and the co-application with biochar clearly improved the soil and the tree health. And at the same time, our result also supported that soil health, especially microbial function, tracks tree performance well. Okay.
Sorry, go ahead.
Okay. And a multi-dimensional indicator set, including the microbial function, is necessary for like a daily monitoring of a street tree management. Also, single amendment are limited, as we discussed. Co-amendment can leverage strengths and mitigate the weakness. But the limitation of our study still exists. Our experiment is still only a short-term observation and only include one type of street tree species. But and the future work should focus on more like a long-term and large-scale monitoring, but which is very lucky. We just start a long-term city-scale experiment in the city of Toronto, and that experiment we included multiple tree species and multiple soil conditions. So I'm pretty sure that the data from that experiment can provide better and more insights on biochar and inactivated yeast core amendments. Yeah. So lastly, I would like to thank Sean Thomas, my supervisor, and Adriana, my external supervisor, and also all the people supported me and helped me throughout the capstone and the internships. Thank you guys very much.
Welcome, Gavin. So match made in heaven, local breweries and healthier trees. Sounds good. First, we'll give the first questions to the external supervisors of the city of Toronto. Yeah.
Thank you so much, Ruogu. That was amazing. My first question is, how did you do all of that?
With all the helps and magic.
My question, so firstly, when you mentioned biochar can tie up other nutrients like nitrogen, is it ever specific with what it takes up? And for example, if we apply biochar in a healthy soil, would that potentially do more harm than good? And should we only focus it on those sort of poor soils that are in poor health?
Well, I mean, like, so first of all, it do have a sort of effect like a nitrogen immobilization I mentioned, but like I think like especially in the urban context, I think like I also mentioned like compaction, right? Compaction is definitely a very big issue in the urban context, and like biochar, we apply biochar provide, for me it's kind of like a provide more physical soil structure improvement, and some other sort of things like microbial stuff or stuff like that are kind of like bonus effect. So to answer your question, like if it will affect the healthy soil, I mean like in the short term, yes, it might, but in the long term, because like the nutrient and water are retained in the biochar, so it's still in the soil. Like compared to if we don't have that one, if we don't have the better soil structure, like the leaching process or like runoff, so we lose them. But with biochar, we can still have them in soil.
Thank you. And then I guess to follow up, would you recommend, so I understand that biochar, it maintains its form for quite some time. You don't really need to reapply it, but what about the biofertilizer, the yeast? Would you need to reapply that? And what would be your recommended application?
Yeah, I mean, I think it depends on the performance of the tree, or like the target, what we really wanna do with all the trees. And that's also kind of my point, is like we have to have a continual monitoring of the street tree. So if we saw some signs of like bad things, yeah, maybe we can apply more bio fertilizer.
Thank you.
Sean, you want to ask?
I can answer a little.
Pass it back. That's all terrific. I wonder, you could just speak moving forward, and you were kind of pressed by our friends in the city to look at these other options.
Oh yeah.
You know, you know, what is out there that can potentially be utilized? And, you know, some of these other options might be good. So I wonder if you could think, you know, there's been a recent work in agricultural system trying to put together decision support systems for making decisions on biochar and other things. And I wonder if you could just speak to how you might envision this going forward and what things might actually be advisable in certain circumstances. That's a challenge.
Okay. Okay. So first of all, as I mentioned, like there's limited information for urban forestry use. Like so we have to set up a more experiment to really understand how, like, let's say how those three options can work in the urban forestry, right? And also another problem here, I think, is some of them are still quite expensive. For example, like the Patterson I searched up from Amazon, and the price was like $70 to $100 for only like 1 kilogram dry powder. So it's definitely not like desirable for large scale application. But I mean, it do need some more research on this one. But we might also have some potential, like maybe we can extract the calcium from like seafood waste or something like that. But we need more study on that. Yeah.
More questions? What? Hang on.
I have a comment from online. It's not a question though.
Go ahead.
Oh, you're waiting for the mic.
Oh, sorry. Please go ahead.
Okay, so this is from Monica Online. It's not a question, more of a comment. Great presentation. I just want to point out that, and I'm probably saying this company name wrong, Lamont
Yeah.
is also a local Canadian company specializing in yeast, bacteria, etc.
Okay. Okay, that's a good question.
Sounded like a product one. Wow. So was there a particular reason you decided to work with exclusively American elm?
Sorry, like what?
Exclusively American elm.
Oh, okay. So I mean, there are two reasons, basic reasons why we choose American elm, or like three reasons. Like the first one is like it is a common street tree species in the city of Toronto, and the second one is kind of like the elms has a very big leaf, so we can measure the indicators more easily, and also American elm has a quite like fast growth, so we don't need to wait too much to get a result. Yeah. So does that answer your question?
Great presentation, Gavin.
Thank you.
I just want to ask about the measurements and the instruments that you're using. Can you kind of speak on what you're doing with that?
Sorry, like what?
Can you kind of speak on like the instruments you're using to take all your measurements and whatnot?
Sorry, I still don't get you very much.
What instruments did you use to take?
Oh, okay. Yeah. So I'm gonna go back to these slides. I think I leave the deep pigment and not like deep pigment, like the pattern response to Zhang, because she's gonna like discuss that more. So I'm gonna talk about like the soil part. So the soil EC and the soil pH, we use the sort of like a electrolytic. I don't really remember the name, but it's kind of like a stick you just stick in in the samples, and it tell you the results. And for the AWCD, I just mentioned like the eco play. And the soil organic matter, we use a Luzon Zhang light leading method. So basically, put the soil sample in the oven for some time, and you get the reduction of mass, and you just calculate the difference in the mass, and you get the soil organic matter content.
Good question. We have time for one more from James.
Thank you for the presentation, and we have also collected a large amount of data on the biochar, and the results show that different application rates of biochar with different soil performances, and the relationship between them is non-linear. So my question is, in your project, what's the dosage of biochar you recommend applying and severely?
Okay, that's a good question. Like in our experiment, we did 40 tons per hectare, and if we apply that into urban context, there might be a unit conversion, but that's a ratio, like 40 tons per hectare. And that one was from a previous study from Zhang and his team as well, and they test a different dosage rate from 20 to 60 or 80, and they found that the 40 tons per hectare is the optimum dosage for plant biomass. So we use that one for our dosage.
Thank you.
Ready. Thank you, guys.